Hello, good evening, everyone. Welcome to the week 12 of the tutorial session of this course, Digital Signal Processing and its application. So, I'm Abhishek Thakur, PMRF PhD student at Indian Institute of Technology, Hyderabad. So, today is the last tutorial session on this course, and we will have one extra session that will be on Wednesday at the same timing. So, today we will discuss questions related to the week 12. So, consider we'll start solving the question. Consider a train of unit impulses. So it is given as Tn is equal to summation k is equal to minus infinite to plus infinite del of n minus kn. So actually this will have an impulse train like this. Okay. So we have to find the nature of the DTFT sequence is. So the discrete time Fourier series sequence is denoted as 1 by n summation n is equal to 0 to n minus 1 Pn e to the power of minus jk omega naught n. Here omega naught is equal to 2 pi by n. So dtft of this will be p of omega is equal to summation k is equal to 0 to n minus 1 2 pi by n del of omega minus k omega naught. So the period will be 2 pi by n because uh, the DTFT of the signal over the extended frequency repeats itself after an interval of 2 pi. It is safe to say that DTFT of the train of impulse will have train of impulses with period 2 pi by n. So also we'll move on to the next question. So consider the statement given as is equal to n by 2 pi x of omega p of omega n is equal to n by 2 pi x of n convolution with p of n. The DTFT of sequence xn denoted by x omega and p omega denotes the DTFT of the sequence p omega. So the given statement can be used to demonstrate the occurrence of time aliasing. Is this assertion true or false? So previously we have find P of omega is equal to, so observe that for ideal sampling we multiply the signal with strain of impulses of unit strength so that the samples of signals are not scaled at any factor. So the frequency representation of the sample signal x tilde omega is equal to n by 2 pi x of omega p of omega. As the train of pulses p omega does not have unit strength, so we can write x tilde n is equal to omega naught xn convolution with pn. So this can be written as omega naught summation of x n minus k of n, where k is equal to minus infinite to plus infinite. So yes, it can cause aliasing because when a continuous time is sampled, there is a possibility of aliasing in the frequency domain. So yes, it can cause the aliasing. So aliasing can be like there will be three cases. Case one, like when omega naught is greater than 2 omega m, then there will be no aliasing. Omega naught is greater than, or sorry, you can either equal to 2 omega m, that is the Nyquist rate, and omega naught is less than 2 omega m, so there will be aliasing here. Okay, wait for a minute. Coming to the next question. Assuming for the moment that xt is continuous time, real and non-negative signal with non-negative real Fourier transform, x omega is greater than or equal to 0. If this is sampled at t is equal to nts, where ts is the sampling time, and if xn represents the sequence of sample, the following statements may be true. So the dTft of xn is given as x of omega, where omega is the normalized angular frequency, or we can denote as omega d. Omega d is the normalized angular frequency. Okay, summation of x omega minus k omega naught, here k is equal to minus infinite to plus infinite. So it is like we can observe that x of omega d is equal to x tilde of 2 pi omega by omega naught. So here omega naught is the sampling frequency. Let me check whether this. So omega naught is the sampling frequency here. So it is given in the question that x of omega is greater than equal to 0, and so x tilde of omega is greater than equal to 0. So we get that x tilde square is greater than equal to summation of x square omega minus k omega naught. Why? Because square is always greater than the sum of square. Square of sum. So here k is equal to minus infinite to plus infinite. So when we apply this integral over the inequality, so minus omega naught by 2 plus omega naught by 2 summation x square omega minus k omega naught, k is equal to minus infinite to plus infinite d omega naught. So this is d omega. So this is equal to summation k is equal to minus infinite to plus infinite. So this we can write it as minus infinite to infinite mod of x omega square d omega. So this is equal to xt square dt, and t is equal to minus infinite to infinite. So using this we can write summation of x of and mod square Ts is greater than equal to mod of xt square dt. Okay, here n is equal to minus infinite to plus infinite. So option A is correct and option B is automatically incorrect. So this signal is band limited and the sampling frequency is greater than the Nyquist rate in the interval of integration that we have chosen. So equality holds if the signal is band limited and sampled at frequency greater than the Nyquist rate. So option C is also correct for this question. So continue the last three problems. Let's xn tilde denotes the sequence whose discrete time Fourier series coefficients denoted by xk are generated by sampling dtft of xn at omega is equal to k omega naught, where omega naught is equal to 2 pi by n and k is 0 to n minus 1. Which of the following statements are true? So with the previous result, we can write as 2 pi by n summation of n is equal to 0 to n minus 1 mod of xn square is greater than equal to 0 to 2 pi mod of x omega square d omega. So option A is the correct answer for this question. So also when time aliasing does not occur, a similar result as before as we obtained. So equality holds if time aliasing does not occur, and we can directly obtain the answer for this question with suitable modification from the previous questions with the principle of duality. Now coming to the next question number fifth. So making use of the solution from the previous statement, which of the following conclusions are false? So from the solution of the previous questions, it is clear that the aliasing can be prevented if the signal is time limited and DTFT is sampled at a sufficiently high frequency. So the signals in general cannot be band limited and time limited at the same time. So this option is true. Signals in general can be band limited and time limited at the same time. So this is false. So actually this is false. So this will be the correct answer for this question. Time aliasing may be prevented if the signal is time limited. This is also true. Periodic is period. This is also true. So option B is the correct answer for this question. So now there is a problem on the discrete Fourier transform. So the endpoint DFT of a endpoint sequence is denoted by xk is equal to n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi k by n into n. So we have to answer like consider 4n point sequence yn defined as yn is equal to xn for all n is 0 to capital N minus 1 and yn is equal to 0 otherwise. If yk denotes the 4n point DFT of yn, then xk is equal to y4k. So we have to find whether it is true or false. So I will write it here. So we have to answer is it true or false. So yk is equal to summation n is equal to 0 to 4n minus 1 yn e to the power minus j 2 pi k divided by 4n into small n. So this will become summation n is equal to 0 to n minus 1 x of n e to the power minus j pi k by 2n into n. So from this we can easily follow that x of k is equal to y of 4k. So this is true. So for the previous question, the answer is true. Now we will move on to the next question. So now consider another 4n point sequence z of n defined as zn is equal to xn for all n is 0 to n minus 1 and zn is equal to x n minus n for all n is 2n to 3n minus 1 and zn is equal to 0 otherwise. So if zk denotes the 2n point DFT of zn, then which one is the correct? So zn is equal to yn plus yn minus 2n. Is implied that zk is equal to yk 1 plus it will become e to the power of minus j 2 pi k and divided by 4n. So this will become yk 1 plus minus j to the power of k. So from this we can follow that z of 4k is equal to 2y because when you substitute then we will get 2y 4k and this is also is equal to x of K. So, sorry, 2 of x of k. So option C is correct. And z of 2k plus 1 will be 0 because 1 minus 1 will be 0. So it will become option B is also a correct answer. Let xn be a 4-point sequence. X is equal to x0, x1, x2, x3 of transpose, and small x is equal to x0, x1. So where the T denotes the transpose here. In this vector format, the equation that connect the sequence vector x with DFT of vector x can be put down in a matrix form. So where M is a squared matrix, choose the correct option. So we have to find the magnitude of determinant of M. So we can write like xk as an input sequence and compute the n point DFT of this sequence. We can easily write xk is equal to summation n is equal to 0 to capital N minus 1 xn e to the power of minus j 2 pi k n by n. So this can be written as e to the power of j 2 pi n minus k. So this we can write it as n x of n minus k. So which means applying the DFT operation on the entire array simply inverts the endpoint sequence xn. So if we apply the DFT operation on x of n minus k and again on its DFT, we can easily observe that result is n squared x of n. So the m to the power of 4 x is equal to n squared x because DFT of x of n minus k. So this results in n squared x of n. Okay. So which like now this looks like an eigenvalue equation of type. So the eigenvector x can be anything arbitrary. We can see that m to the power of 4 will be n squared in, where in is identity matrix of order n. So determinant of m to the power of 4 is equal to n to the power of 2n. So for n is equal to 4, So determinant of m, that is equal to n by 2. So that is equal to 4 to the power of 2. That is equal to 16. Option D is the correct answer. So now let's take some question. Find the 4-point DFT of sequence x of n is equal to 1 by 3 for n is 0 to 2. Okay, and it is 0 otherwise. And we have to plot the angle of the response x of k. Okay, so x of k will be here. Know that that is summation n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi k by n into small n. So from here we can write x of k is equal to, here capital N is 4, so n is equal to 0 to 3 x of n e to the power of minus j 2 pi by 4 kn. Okay, so if n is equal to 4, then k is equal to 0, 1, 2, 3, like up to capital N minus 1. So xn in this question is 1 by 3, 1 by 3, 1 by 3, 0, 2, and 0. From here we can derive. Xn is given like this. Okay. So now we have to find our xk. So xk is equal to, first we substitute n is equal to 0. So that will become 1 by 3 plus 1 by 3, n is equal to, for 1 it will become e to the power of minus j 2 pi by 4 k. Then for n is equal to 2, it will become 1 by 3 e to the power of minus j pi k. And for n is equal to 4, it will become 0. Okay. So what is our x of 0? So x of 0 will be 1 by 3 plus 1 by 3 plus 1 by 3. Okay. This will 1 and angle 0 degree. X of 1, what it will be become? So x of 1 is equal to 1 by 3 plus 1 by 3 e to the power minus j pi by 2. So this will become minus j plus 1 by 3 e to the power minus j pi k, minus j pi. So this will become again minus 1 plus 0. So x of 1 will be minus j by 3. Okay. For this was for k is equal to 1. This was for k is equal to 0. Now for Now for k is equal to 2, x of 2 is equal to 1 by 3 plus 1 by 3 e to the power of minus j pi plus 1 by 3 e to the power of minus j 2 pi. So this will become 1 by 3 plus minus 1 by 3 plus 1 by 3. This will become 1 by 3 again. And for k is equal to 3, x of 3 will become again 1 by 3 plus j by 3 minus 1 by 3. So this will become j by 3. So now the phase spectrum, what is asked in this question? X of 0, phase spectrum is 0 degree. For k is equal to 1, it is minus j by 3, so it is minus pi by 2. For k is equal to 2, again 0 degree. For k is equal to 3, again j by 3, so it is pi by 2. So now let's solve one more tricky question. Find inverse discrete Fourier transform IDFT of x of k is equal to 1, 0, 1, 0. So here x of n is given as the inverse Fourier transform 1 by n. X of k, here k is equal to 0 to n minus 1 e to the power of j 2 pi by n kn. So n is 4 here, so we'll substitute 1 by 4. So k is equal to 0 to 3 x of k e to the power of j 2 pi by 4 kn. Okay, so this can be written as 1 by 4. For k is equal to 0, it will become 1. For k is equal to 1, it is 0. For k is equal to 2, it is become 1 into j pi n. So e to the power of j 2 pi by 4 into 2 of n plus 0. So this is x of n is our 1 by 4, 1 plus e to the power of j pi n. So here this we can write as 1 by 4, 1 plus e to the power of j pi is minus 1. So minus 1 to the power of n. Okay. So now x of 0, if you substitute n is equal to 0, it will become 2 by 4. So it will be half. For n is equal to 1, x of 1, it will become 0. For n is equal to 2, x of 2, it will become again 2 by 4, half. For n is equal to 3, x of 3, it will become again 1 by 4, 1 minus 1, so it will become 0. So what is the sequence x of n? Half, 0, half, and 0. So now we'll solve one more question. The first 5 points of the 8-point DFT of a real valued sequence are 5, 1 minus J3, 0, 3 minus J4, and 3 plus J4. Okay. The last 2 points of the DFT are respectively. So for this question, so it is given that xn is real and xk is the conjugate symmetry. Because we know that if xn is real, and xk will be the conjugate symmetry. So x of k is equal to x conjugate of n minus k. Here n is equal to 8. So x of k is equal to x conjugate of 8 minus k. So x of 6, when k, we have to find the last 2 points of the DFT, that is x of 6 and x of 7. So x of c is equal to x conjugate of 8 minus 6, x conjugate of 2. So that is 1 minus J3 conjugate, so it will become 1 plus, sorry, 5 comma 1 minus J3, 0. Sorry, this is 0th index, first index and second index. So it is the conjugate of 0, so it will become 0. Now x of 7, that is equal to x conjugate of 8 minus 7, so that is equal to x conjugate of 1. So this is equal to conjugate of 1 minus J3, so this is becoming 1 plus J3. Okay, in this way we can find. Now let's solve one more question. Consider x1n is given as 1, 2, 3 and 0. X2n is given as 1, 3, 2, 1. Let x1k comma x2k be 4-point DFT of x1n and x2n. X3n is inverse of x3k, that is given as x1k into x2k. So find x3 of 2. It's a very good question. So we know the periodic convolution thing. it is a question of periodic convolution. So in this, if x1n have the DFT as x1k with period n0 and x2n, the DFT of x2n is given as x2k with period of n0, then the periodic convolution of x1n and x2n, and the DFT of this is given as x1k, x2k with period n0. The same concepts we will apply here. So x1n periodic convolution with x2n. Now DFT of this is given as x1k, x2k. What is x1n? 1230. So x1n we can write as here 1, 2, 3, 0. Okay. And x2n is equal to what is given? 1, 3, 2, 1. 1, 3, 2, 1. So what is x3 of 2? So this is equal to 1, 2, 3, 0 cross 1, 3, 1, 2. So now when we do x3 of 2, we will get as 6 plus 3 plus 1 into 0 plus 2 into 1. So what will be the answer? It will be 11. Okay. So now we will see proof Parseval's relation that is given as energy of a signal is n is equal to 0 to capital N minus 1 xn, that is equal to 1 by n k square. So we know that first of all x of n, this is written as 1 by n summation n is equal to 0 to n minus 1 xk, that is I dft, e to the power of j 2 pi by n small kn. Okay. So now we'll take conjugate. So X conjugate of n is equal to 1 by n summation n is equal to 0 to n minus 1 xk e to the power of minus j 2 pi by n kn. So summation of n is equal to 0 to n minus 1 mod of xn squared. This is given as summation of n is equal to 0 to n minus 1 xn dot xn conjugate. So this can be written as n is equal to 0 to n minus 1 xn. Next, x conjugate of n is written as 1 by n summation of xk e to the power minus j 2 pi by n kn n is equal to 0 to n minus 1. So this we can write as 1 by n, sorry, here also conjugate is there, x conjugate k, and we'll take xn inside. Xn k is equal to 0 n minus 1, here n is equal to 0 to n minus 1 e to the minus j 2 pi by n kn. So this will become 1 by n because this is again our x of k. So this we can write as 1 by n summation of mod of xk square. Okay. So now we will see also the fast Fourier transform. So the endpoint DFT is given as x of k is equal to summation of n is equal to 0 to n minus 1 x of n e to the power of minus j 2 pi by n kn. Okay. So to compute one point DFT, it is required n multiplication and n minus 1 addition. So to compute one point DFT, it requires n squared multiplication and n multiplication and n minus 1 addition. So to compute n point DFT, it requires how much? N square multiplication and n into n minus 1 additions. Okay. So the computation has increased. So they have the fast Fourier transform. FFT reduces the number of multiplication to n by 2 log of 2n and number of additions to n into log of 2n. So there is butterfly structure and there is different way to compute FFT. So generally FFT reduces the complexity. So that's why we are using it. So today we'll end the lecture here only. So thank you everyone for attending today's class. We'll again meet in the extra session on the Wednesday. And so that will be the final class on the Wednesday. That is the extra lecture. So if you have any doubt, you can ask. And also this video is recorded and it will be uploaded on the YouTube. So if you have any further doubts, you can ask in the comment section of the YouTube. There also we will reply if you have any doubt. So today we will end up here only now. So thank you. Bye bye.